This slide shows the mechanical properties of the perovskite materials. So this table shows the key mechanical properties such as Young's modulus and the hardness of the perovskite material. You can see that the perovskite material has the Young's modulus in between the organic polymer and the conventional inorganic ceramic materials. So this Young's modulus describes the relationship between the applied stress and the resulting strain of the crystal lattice. So with the lower Young's modulus, we can use the materials for flexible or stretchable materials. For the case of conventional inorganic materials, we can achieve the high efficiency and stability of the device owing to the excellent optoelectronic properties, but its mechanical property is not good because it is brittle, and also it is very expensive because we should process the material at high temperature and vacuum. On the other hand, the organic material has good mechanical property. We can use it for flexible and stretchable materials, but still the material cost is quite expensive. And importantly, the optoelectronic properties is relatively poor. For example, the mobility of the organic material is relatively poor compared to the inorganic materials. But for the case of perovskite material, it can achieve highest efficiency, although the stability still is the problem. And we can take the advantages of good mechanical properties of the perovskite materials. So we can fabricate the flexible solar cells. As you can see in this graph, they shows that with the bending cycle over 10,000 times, you can see that there is almost no performance degradation of the perovskite solar cells. And they even construct the solar cells that can be crumpled, as you can see here. And you can see that with the crumpling, still almost no degradation of the performance over 100 times. And let us talk about the defect chemistry in the perovskite materials. As we saw in the previous slide, the perovskite material can be synthesized at low temperature. It means that the energy required to construct the chemical bonding is relatively low. It is beneficial for the low temperature process, but in other words, it means that we may require low energy to break the bond as well. So the energy required to generate the defect, such as the Ma vacancy and lead vacancy and iodide vacancy, was calculated to be very low. You can see that it is only around 0.1 to 2 electron volt per defect. And for comparison, you can see that the conventional oxide material has much higher formation energy for the point defect. But interestingly, the absorbed dark carrier concentration for the thin film perovskite was found to be low, regardless of such high density of the defect, which was due to the self-compensation property of the perovskite defect. It means that the charged defects in the perovskite film interact with each other to compensate their charge, so it does not generate the additional dark carrier in the films. And the other noticeable property of the defect in the perovskite material is its migration phenomena. As you can see in this figure, for example, the vacancy defect here can move to another neighboring atomic site by hopping of the neighboring ions. So, for example, this iodide ion can hop to this defect site, and then at the same time this iodide vacancy will move to this site. And similarly, the lead or the organic cation vacancy move from one side to another side of the lattice. And for the perovskite material, the energy required for such migration was calculated to be as low as 0.6 electron volt. You can see that especially the halide defect migration activation energy is relatively low. And this activation energy for migration of the defect can also be measured by experimental measurement by using the Nernst-Einstein equation. So you can construct the lateral device like this. So this is the perovskite layer, and you put the parallel electrode and apply the bias voltage. Then you can measure the conductivity of this perovskite material as a function of the temperature. And then you can use this Nernst-Einstein equation to calculate the activation energy of the ion migration in the film. And this is the typical data measured from the perovskite thin film. And you can see that there is two regions. The region at lower temperature is related to the migration of the extrinsic defect. Extrinsic defect means that the defect generated during the process of the materials. So because the defect is already exist in the lattice, their migration will require relatively lower energy. So you can see that the energy required for the migration of this extrinsic defect is relatively low, because this slope is relatively small, and at higher temperature, so as the temperature increased, the thermal energy will activate the vibration of the atom, and then the atom will escape from its original site to generate the defect, and then such defect can also migrate. So for the case of this extrinsic defect, it only require energy for just migration. But for the case of this intrinsic defect, it will require energy for generation and then migration. So their activation energy should be much higher. So this region. And you can see that in this case, the activation energy for intrinsic defect is around 1 electron volt. And this figure shows the generation of some conducting pathway in the in between the two parallel electrodes, which is the evidence for the migration of the ion. And from the measurement, the ion mobility in the perovskite material was measured to be around 10 to the minus 9 square centimeter per volt second, which correspond to the 1 micro per second under 1 sun illumination. So it means that the ions in the perovskite film can already travel 1 micrometer in 1 second, which is pretty fast. And migration of this ion in the perovskite film can affect the performance of the perovskite solar cells. So the charge generated in the solar cells should be collected through the built-in electric field. So for example, if we generate the electron and hole here, they will be collected through the built-in potential. But if there is some moving charge, moving ions in the materials with some specific charge, it will react to the built-in electric field in the device. So for example, the positively charged ionic defect in the perovskite material will move towards this direction because of the electric field. So this is the built-in electric field. But as the discharged ion move towards this direction, they will accumulate at this region, and then will generate the electric field to the reverse direction. So the electric field generated by the accumulated ion will be in this direction. So this electric field generated by the accumulated ion will cancel the built-in electric field in the device. So you can see that the band bending in the device is distorted, and in that case, the charge generated at the bulk region will not have sufficient driving force for collection. So the collection efficiency of the charge in the device will be degraded. So as a result of the ion accumulation, the current voltage hysteresis effect is observed from the device. So we can scan the device of the we can scan the current voltage characteristics of the device in two different directions. For example, if we scan it from the this open circuit voltage to the short circuit condition, we refer it to the reverse scan, and the scan with the opposite direction is defined as a forward scan. On the open circuit condition, the band in the device should be flat, so there should be no current flow. So, but as we go towards the short circuit condition, at short circuit condition, there should be the band bending generated by built-in electric field, so Pi, so that the almost all the charge carrier generated in the device can be collected. But for example, for the case of reverse scan, if we switch from this open circuit condition to short circuit condition, on the open circuit condition, because there was no built-in electric field, so there should be no moving ionic defect in the device. But as we switch it to the this short circuit condition, now we have some built-in electric field, which should have the direction from here to here. Then this built-in electric field will cause the movement of the ionic defect in the device. So the plus charged ionic defect will be accumulated at this side, and the minus charged ionic defect will be accumulated at this side, which will generate the opposite direction electric field. So it will cancel out this built-in electric field. So the in fact, as we go from the transient state to the steady state, where the redistribution of the ion is completed, the built-in electric field will be reduced because of the field generated by the accumulated ion. So the real real band bending after the accumulation of ion will be something like this, where the built-in electric field is decreased because of the E field generated by the ion. And as a result, the charge collection efficiency will reduce, which will reduce the current density generated from the device. So that is why for the case of reverse scan, you can see here. So as we change the voltage from one point to the other point, you can see that there is a gradual decrease in current density, which is due to the redistribution of the ion. But usually for this kind of IV measurement, we set some specific time to get the signal from this current signal. So, for example, if we set the time to get the current data from the device to be around this point, around 200 seconds, which is not realistic, but let's say if we set here, it will actually overestimate the device current, because in reality, the stabilized current density should be lower than this transient current density. So generally, for the case of reverse scan, it overestimate the device current, whereas for the case of forward scan, it is completely different situation. So in this case, there should be already the accumulated ion, and this accumulated ion is decreasing the charge collection efficiency. And as we switch to the open circuit condition, the effect of this accumulated ion will be removed, which will enhance the current density of the device. So for the case of Ford scan, you can see that as we switch from one bias voltage to the other bias voltage, the current density is gradually increased. So in this case, if we get the signal at early stage of the this measurement, we will underestimate the device photocurrent. So for the case of Ford scan, it usually underestimates the device photocurrent. So usually we should consider the both forward and reverse scan, and usually realistic device efficiency should be in between this reverse scan and forward scan. So this kind of current voltage hysteresis make it difficult to accurately measure the device performance of the perovskite solar cells. And another effect of the moving ionic defect is its doping effect. If we have some impurities, it can act as a dopant in the materials. So similarly, the moving ionic defect in the perovskite material can act as a dopant. For example, the Ma vacancy can act as a p-type dopant, whereas the Ma ions can act as a n-type dopant. So if we apply the bias with the bias where the Ma vacancy and Ma ion exist, this Ma vacancy should have the minus charge, whereas this Ma ion should have the plus charge. So with applied bias, they will move to some specific region to cause the doping effect. So by applying the bias, so we can form this kind of homojunction of the perovskite materials. So this kind of homojunction generated by self-doping effect can also be used to construct the solar cells, as you can see here. But of course, this kind of doping effect will not stable because their activation energy for migration is relatively low. So if we remove the applied bias, they will go back to the original site to remove the doping effect. And let's see the effect of the defect density and illumination on the activation energy of the migration of the defect. So this graph shows the activation energy measured from the films under different conditions. First of all, we can see that the films with a larger grain has relatively higher activation energy for migration of the ionic defect. This is because with a larger grain, the grain boundary region should be relatively smaller than the films with a smaller grain, which means that there should be relatively low defect density. So the defect in the film can migrate itself, and it can also act as a migration pathway of the generated defect. So if we reduce the density of the defect, we can increase the activation energy for migration in the film. And another phenomena is that if we apply the illumination of the light to the film, we can see that the activation energy is significantly lowered, and this is because the effect of the generated charge on the illumination. So as you see in this figure, for migration of some specific ion towards the another neighboring defect site, it should overcome the electrostatic interaction with their original site. So for example, this is the I minus. There should be plus charge in the vacancy site. So there should be some electrostatic interaction. But this electrostatic interaction can be screened if there is an electron here, which has the minus charge. So this photogenerated electron can screen the plus charge of the iodide vacancy. So this iodide ion can easily move to the neighboring site. Similarly, the charge of the organic cation can be screened by the plus charge of the photogenerated hole. So this is why the activation energy for ion migration is lowered on the illumination condition. And this kind of ion migration phenomena can affect the device stability at longer term. So if the ion, as you can see, move towards the interface, of course the local stoichiometry will be destroyed, and then this ion can, in longer term, can penetrate into the neighboring layer, so which can cause the degradation of device performance. So this graph shows the evolution of device efficiency under operational condition. You can see that there is very fast initial decay of the device performance, which is because of the redistribution of the ionic defect in the device, which will reduce the charge collection efficiency and increase the series resistance of the device. And then there is a slower decay of the device performance. It is generally because of the penetration of such defect towards the neighboring selective contact layer. The first fast initial decay is actually reversible degradation, because if we remove the light, the built-in electric field in the device will be removed, which will cause the reversible redistribution of the accumulated ionic defect at the interface. So you can see that if we have the initial decay and then remove the light, then start the measurement again and again, you can see that it is recovered to the initial performance. On the other hand, the slower decay at longer time scale is the not reversible degradation. So it is permanent degradation because this kind of penetration of ionic defect towards the neighboring contact layer will cause some chemical reaction, which is not reversible. So this kind of longer time scale degradation is not reversible, but permanent degradation of the device. So for this issue, right now the stability is very critical issue for commercialization of the perovskite solar cells. So you can see that the device efficiency is comparable with the commercialized silicon, and the cost is expected to be lower compared to the silicon solar cell because of the lower process temperature and the solution process. So then how can we improve the stability issue? So as we learned in the previous slide, we saw that the perovskite film processed at low temperature using solution process is polycrystalline in nature, and it should contain high density of the defect because of the low formation energy of the defect. Then we should improve the crystallinity of this perovskite film to reduce the defect density. So if we see the crystallization process of the perovskite film, so as we spin coat the solution, wet film will be formed. And then as we heat the wet film, there should be some evaporation of the solvent. Then the concentration of solution will increase to reach certain concentration where the supersaturation of the nuclei occur. And this formed nuclei will grow until they will contact with the neighboring crystal, or the older precursor solution is removed. So if we have the smaller number of nuclei, it will have more time to grow into the larger crystal. So for example, if we have a lot of nuclei, these nuclei will grow simultaneously to form very small grain, something like this. But if we have relatively smaller number of nuclei, these nuclei can grow to form much larger grain size. So we should reduce the nucleation rate of the perovskite film to enhance the crystallinity and thus reduce the defect density. As you see in this slide, the nucleation rate, according to the classical nucleation theory, is dependent on critical Gibbs free energy. This Gibbs free energy is the energy barrier for the formed nuclei to be stable without redissolved in the solution. And this critical Gibbs free energy is a function of temperature and degree of supersaturation, and surface free energy and molar volume. And we can actually control the degree of supersaturation by controlling the molecular interaction between the perovskite material and the precursor, between the perovskite precursor and solvent molecules. So if we induce the stronger molecular interaction between the perovskite precursor and solvent molecules, the degree of the supersaturation will reduce, which will increase the critical Gibbs free energy to reduce the nucleation rate. Then, how can we control the interaction between the perovskite precursor and solvent molecule? Perovskite precursor, such as lead iodide, is Lewis acid because the lead here has the empty valence shell because it only contains 6 valence electron in its outermost shell, so it can accept the electron from the Lewis base. So this Lewis acid lead iodide, for example, can accept the electron from the Lewis base DMSO. This the DMSO has the lone pair electron on its oxygen, so there should be some partial negative charge on this side and partial positive charge. So this partial negative charge can interact with the Lewis acid lead iodide. So similarly, the iodide ion in the solution can also interact with the lead iodide by donating its negative charge. So if you make the perovskite solution, for example, if you dissolve the lead iodide itself into the DMF, its solubility is actually not that good in the DMF solvent. But if you add some iodide or if you add some Lewis base, such as DMSO or NMP, it can interact with the lead iodide to through the coordinative covalent bond, which assist in the solvation of lead iodide. So if you add some iodide or Lewis base, you can see that the solubility of lead iodide in the solution is significantly enhanced. And such lead iodide coordinated by some solvent molecule or the iodide molecule can be absorbed from the absorption spectrum. So each lead iodo-plombate molecule has some specific absorption peak observed from the absorption spectrum. So this kind of molecular interaction between perovskite precursors and Lewis base can be used to form some intermediate phase for film fabrication. So for example, if we add the MAI, lead iodide, DMS, so here MAI is the methylammonium iodide. So methylammonium is described as MA here. So this perovskite precursor interact with the Lewis base DMSO to form some intermediate adductive film. So you can remove some solvent from the solution by treatment of some specific washing solvent, such as diethyl ether. For example, diethyl ether is selectively dissolved out the DMF. So the resulting film contain only the MAI, PBr2, and DMSO, which is the Lewis excited base adduct. And then as we heat this adduct film, the DMSO is slowly removed out from the film, and then we can form very uniform and the dense methylammonium lead triiodide film. Then in this process, the crystallization and thus the nucleation and growth process will be dependent on the molecular interaction between this Lewis-based DMSO and perovskite precursors. So if we strengthen the interaction between this solvent molecule and perovskite precursor, we can slow down the crystallization process by enhancing the critical gypsum-free energy for nucleation. So, for example, if we replace the DMSO with the urea, which has higher dipole, so the negative charge on this oxygen should be stronger, so it can form stronger interaction with the perovskite precursors, which can slow down the nucleation rate. So as you can see here, so if we heat the film with the DMSO and the film with the addition of urea, you can see that the film with the DMSO completely changes to the black color in few seconds. So this is after few seconds, but you can see that the color change for the films with urea is much slower, which means that the nucleation rate in the film is much slower. So as you can see, as a result, the resulting grain size of the film is much larger than the films with the DMSO. And another interesting thing is that the added urea is formed at the grain boundary region. And this is because in the wet film, the DMSO adduct with a relatively lower energy barrier for nucleation first to form the grains, and then the remaining urea adduct with a relatively higher energy for higher activation energy for nucleation will formed at the grain boundary region. And because of the electron donating property of the urea, it was found that it can passivate the defect such as the iodide vacancy, which will have the plus partial charge. So the urea with the electron donating property at grain boundary region can passivate this kind of grain boundary defects. And this kind of interaction is the dipole-dipole interaction, and it was confirmed from the FTIR measurement. And as a result, the measured defect density was significantly reduced. But as we discussed in the previous slide, then this kind of passivation by small molecule can enhance the stability of the device, but actually it was found that this interaction between the small molecule defect passivation agent and the perovskite crystal is relatively low, so their interaction can be easily broken under harsh operational conditions. So recently, the researcher tried to replace the conventional small molecule additive with the polymeric additive. So for example, we can incorporate polymeric Lewis base, such as the polypropylene carbonate. So this kind of polypropylene carbonate with the Lewis base functional group on its repeating unit will have a lot of Lewis base functional group in their molecule. And each Lewis base functional group can interact with a lot of precursor molecules to form so-called macromolecular intermediate phase. So this kind of macromolecular intermediate phase can be crystallized in between the grain. So you can see that there is some bridge between the grains of the perovskite. So this bridge consists of perovskite and polymer composite. So it can transport the photo-generated charge from the grain to the other grain. Different from small molecule, where each small molecule interact with the perovskite crystal. And this, as I discussed in the previous slide, this dipole-dipole interaction is weak secondary chemical bonding, so it can be easily broken. For the case of polymeric Lewis base, however, the Lewis base functional group in its repeating unit will interact with a lot of perovskite crystal. So the total energy of the interaction should be much stronger than the interaction formed by each small molecule. So it can form a much stronger interaction, and it should be more durable compared to the interaction with the small molecules. So as a result, addition of the polymeric Lewis base can improve the device performance as well as the device stability. You can see that the device with a polymeric additive has relatively good device with polymeric additive has relatively better stability. For the case of the perovskite crystallization, because we directly form the films on the substrate, in fact, there should be active heterogeneous nucleation process. So this heterogeneous nucleation can be described by introducing the correction term pi here. So depending on this correction term, the energy barrier for nucleation in presence of heterogeneous nucleation is significantly changed. So this correction term pi is calculated by this equation. Here, the theta is the contact angle of the solution on the substrate. So the contact angle of the solution on the substrate can be measured by this. So here, the contact angle is the degree between this line and the substrate. So this is the contact angle. And you can see that as we decrease the contact angle, which means that if the solution has good wettability on the substrate, the pi, the correction term for heterogeneous nucleation, is significantly decreased, which means that the energy barrier for nucleation of the perovskite material will significantly reduced. So you can see that here, as the contact angle of the perovskite solution decrease, the nucleation barrier decrease. So the nucleation become very fast. So the resulting grain size is decreased. And the perovskite film can be also formed by two-step sequential method, where the lead iodide is first spin coated, and then the organic iodide is spin coated on top of the lead iodide, and then the heat treatment can cause the interdiffusion of the precursor to form the perovskite layer. And in fact, when we spin coat the organic iodide, there is already some reaction between this organic iodide and lead iodide, and the reaction rate and thus the nucleation rate will dependent on the concentration of this organic iodide. So if we use the organic iodide solution with a lower concentration, the reaction rate will be slower, so a relatively smaller number of the nuclei formed. So the resulting grain size is bigger than the case with the higher concentration. So as you can see, with higher concentration, a lot of nuclei formed, so they cannot grow into the larger grain. And recently, the incorporation of 2D perovskite is widely explored. So if we replace the organic A cation in the three-dimensional perovskite with a much larger organic cation, such as penethylammonium iodide, this corner sharing octahedral cannot be maintained, so they start to split like this to form the two-dimensional perovskite materials. So this two-dimensional perovskite material has relatively poor optoelectronic properties because there is insulating large-sized organic cation in between the charge transporting inorganic octahedra. But their stability is relatively better than the three-dimensional perovskite because it is consist of the A cation with relatively larger alkyl chain, relatively longer alkyl chain, as well as the hydrophobic aromatic ring. And importantly, they have relatively higher energy barrier for nucleation. So if we add small amount of 2D perovskite into the solution, first 3D perovskite is formed because of relatively lower nucleation barrier, and then the 2D perovskite is formed at the grain boundary region. So from TEM measurement, you can see that this grain interior region consists of 3D perovskite, whereas this grain boundary region consists of 2D perovskite with a relatively larger lattice parameter. And this TM image more clearly shows the surface 2D perovskite in this region. So this is the 2D perovskite, and this is the 3D perovskite region. So this 2D perovskite, as I mentioned in earlier slide, has relatively better stability against the moisture compared to the 3D perovskite. So it can protect the 3D perovskite from the moisture. So you can see that the films with the 2D perovskite has better stability under very high humidity condition. And the band gap of this grain boundary 2D perovskite is relatively larger. So it can form this kind of type 2, type 1 band alignment. So the charge inside the grain can be repelled from the defective grain boundary region. So as a result, the photoluminescence lifetime, which is closely related with the charge carrier lifetime in the film, is significantly enhanced from around 80 nanosecond to over 1000 nanosecond. So with the 2D perovskite, you can see that the power conversion efficiency is much higher than the conventional bare 3D perovskite. And in this study, they also measure the activation energy for ion migration. You can see that with the addition of 2D perovskite, the activation energy for ion migration is much greater than the bare 3D perovskite. This is because the grain boundary defect is passivated by this grain boundary 2D perovskite. And because of the passivation effect, the activation energy for ion migration is significantly enhanced. And then as a result, the device efficiency is also improved with the addition of 2D perovskite. So you can see that the lifetime of the device is improved more than twice. And in fact, the migration of ionic defect in the device is also dependent on the acyl because as I mentioned in the earlier slide, the migration activation energy for halide is much lower than the organic acation or the lead. So this halide anion is interacting with the acyl at the cubo-octahedral site. So if the interaction between the acyl and halide anion is stronger, the migration of this halide anion can be suppressed. So if we use different organic acyl, the activation energy for ion migration will be changed, and then as a result, the device stability will be also affected. According to the previous research, the Fa cation, formamidinium cation, can form stronger interaction with the surrounding halide anion. So you can see that the device stability of the perovskite solar cell with the formamidinium cation is better than the device stability of the methylammonium cation. And while this organic cation forms the hydrogen bonding with the surrounding halide anion, so this is the hydrogen bond. The cesium cation forms the primary ionic or covalent bond with the surrounding halide anion. So their interaction should be much stronger. So as a result, you can see that with the addition of cesium cation, the stability of the device is significantly enhanced. And let us see some example of the study to demonstrate the effect of cation on the device stability. So this study compared the three different organic cation, the acetamidinium, methylammonium, and guanidinium. So for the case of this guanidinium cation, it can form a larger number of effective hydrogen bonding with the surrounding halide anion. So as a result, you can see that this is the activation energy for ion migration. You can see that the activation energy for ion migration with the guanidinium cation is much higher than the activation energy for the perovskite with the methylammonium ion. So here they calculate the activation energy for ion migration with the assumption that the 25% of the methylammonium is replaced with guanidinium or acetamidinium in the methylammonium lead 3 iodide perovskite. But one thing you can notice is that although the effective hydrogen bonding between the acetamidinium and halide anion and the methylammonium cation with the surrounding halide anion is same. So this is the number of effective hydrogen bonding. Although they form similar degree of hydrogen bonding with the surrounding halide anion, we can see that the activation energy for ion migration become much higher with the addition of acetamidinium anion. This was found to be due to the static effect. So as you see here, the size ionic radius of acetamidinium is much larger than the ionic radius of methylammonium cation. So with the acetamidinium cation, the lattice is expanded, as you can see here, compared to the case with the methylammonium cation. So if we want to, if the ion in this site, behind this lead site, if there is some halide anion, if such halide anion want to migrate from one side to the other side with the acetamidinium, there you can see that their migration pathway is distorted. But for the case of the methylammonium cation, you can see that their migration pathway is very straight. And this is why the activation energy for ion migration become larger with the addition of acetamidinium cation. So this is the calculation. Actually, if we see the measured data, so this is the activation energy for ion migration measured from the pure methylammonium lead triiodide perovskite. And this is the activation energy for films with the addition of acetamidinium cation. You can see that the films with acetamidinium cation has greater activation energy for ion migration. And as a result, the device stability on the one-sun illumination is improved. And also the device stability at high temperature is also improved. Usually the degradation of perovskite solar cell at high temperature is also induced by the ion migration, because if we apply some thermal energy to the film, the thermal energy will contribute to the migration of ionic defect in the film. So the degradation is accelerated. But you can see that the accelerated degradation is relieved with the addition of acetamidinium cation. So as you can see in this kind of study, the molecular interaction between the organic A cation and halide anion will play a crucial role in determining the stability of the perovskite solar cells. So recently, various organic and inorganic cation is studied, and you can see that dependent on the different organic cation, the activation energy for ion migration is changed significantly. Okay, so thank you for taking this long lecture. I hope this lecture is helpful for your comprehensive understanding on perovskite solar cells. If you have any question regarding the lecture contents, feel free to email me at any time. Thank you.